Application of biopolymers in the textile industry. This paper I presented in 14th Asian Textile Conference at Hongkong Polytechnic University, Hong Kong during 27 to 30th June 2017. This slide shows 4 photographs. First one is the conference building of Hongkong Polytechnic. It is a peculiar structure. Second one is the opening ceremony of the 14th Asian Textile Conference. There is participation from various parts of the world. Third picture is my presentation, and fourth picture is of Professor John Jing, HOD of the Textile Department of Hong Kong Polytechnic University during banquet. Biopolymers are produced from natural sources and not produced from petroleum. They are bio-based and or biodegradable. Recently, they are produced by living organisms, that is biologically. They may be thermoplastic or thermosets. They may be composites or homogeneous. Often they have a well-defined chemical structure. Ideally, they are carbon neutral, that is, neither they contribute nor they reduce the amount of carbon in the atmosphere. They hardly cause any carbon emission during manufacture. 1% of the total polymer produced globally is biopolymer during 2015. In 2012, total biopolymer globally produced was 1.5 million tons. It is expected that in 2018 it will reach to 6.7 million metric ton. It is expected that growth of biopolymer production will be 3-4 times in next 7 to 8 years. Methods of manufacture of biopolymers. 3 ways biopolymers can be produced. Firstly, directly extracted or removed from biomass. Secondly, produced by microorganism or genetically modified bacteria by fermentation, followed by polymerization or direct bacterial fermentation processes. Thirdly, it can be produced by classical chemical synthesis from biomaterials. Merits and demerits of biopolymer. Merits. Biopolymers are made from natural resources. They are fully bio-based. They are sustainable, carbon neutral and renewable. Biopolymers are biodegradable and some are compostable. Biopolymers require less petroleum fuel for their production, lesser greenhouse gas emission during biopolymer production. For NGO, a polylactic acid fiber made by natural work, there is 60% less emission of greenhouse gas and 50% less use of non-renewable energy during their production. Now the demerits. Demerits of biopolymers are when biopolymers are produced, they share biological resources which are used for food and fuel. Additional sorting is required during recycling to avoid contamination. Processing is difficult than petroleum-based products. Performance of biopolymers are still inferior than oil-based polymers. They have poorer heat and moisture resistance. Mechanical properties and crystallinity of biopolymers are poor in general. They can be improved by plasticizers. Consumption of biopolymers in tons in the year 2011. In construction works, 2000 tons, medical field, 4000 tons, which include drug delivery systems, wound closure or healing products, surgical implant devices, biosorbable scaffolds, that is temporary support, tissue engineering, hygiene and protective clothing. Food containers bottling, 377,000 tons, waste bag and packaging, 438,000 tons, soil retention sheeting or technical use, 104,000 tons, agriculture film, 61,000 tons, non-oven in agriculture filtration, 61,000 tons, other 27,000 tons. Application of biopolymers. Major application is in packaging and bottles. In composites are combination of two or more materials act as a single material. Like wood is a composite of cellulose and lignin. Sustainable bio-nanocomposites, suitable matrices, for example, aliphatic polyester, polypeptides and proteins, polysaccharides, polynucleic acids, and fillers like nanotubes, nanofibers, clay nanoparticles, hydroapatites, and metal nanoparticles. Bio-nanocomposites are recyclable and stable during use. Worldwide percentage use of biopolymers in various applications in the year 2011. Maximum use in packaging 37.7%, followed by bottling 32.5%, technical use is 9%, catering 7.1%, consumer product 5.6%, agriculture 5.3%, others 2.3%, medical 0.3%, construction 0.2%. Key qualities as healthcare products. They should be bacteriostatics, inhibiting growth of bacteria, fungistatics, that is inhibiting growth of fungi, antiviral, that is inhibiting growth of virus. They should be non-toxic, high absorbent, non-allergic, breathable, hemostatic, that is stop bleeding, biocompostable, compatible, and good mechanical properties. Various biopolymers used in medical applications. Application wound care, polymers used are polyethylene glycol and agar, xanthan, methyl cellulose, CMC, alginate, hydronon, and other hydrocolloids. Application drug delivery, pharmaceutical, starch, polyvinyl pyridinone, polyacrylic acid, ketone, acrylic acid. Application dental material, hydrocolloids, tissue engineering implants, hyaluronan and collagen. Injectable polymeric system, polypectic acids, ketone. Technical products like cosmetics, pharmaceuticals, gum arabic, xanthan, pectin, carrageenan, gelan, wellan, guar gum, locust bean gum, alginate, starch, heparin, chitin, and ketone. Application skin derivatives, highly purified bovine collagen, formalin fixed skin. Hemostatic application, fibrin sealants and foam, ketone and polynacetyl glucomosides gels and ketone adhesives. Application suture, collagen, catgut and Brannan ferulate. Textile application of biopolymers. Biopolymers occupy a relatively low market share in the textile sector due to unsatisfactory mechanical properties as compared to conventional polymers. Difficulty in processing of biopolymers, higher prices of biopolymers. However, some biopolymers have achieved or exceeded the common properties of petroleum-based man-made fibers. There are many applications that they become a true textile alternative in the long run. Research may be widened to include application in interior textiles or in sportswear and other clothing. Classification of biopolymers. Polyhydroconates and polylactic acids are examples of biopolyester. Starch, amylase, amylopectin, cellulose, agar, alginate, carrageenan, pectin, konjac, various gums like guar gum. They are examples of plant and algal polysaccharides. Xanthan, dextran, gelan, leaven, cardinalan, polygalactosamine, bacterial cellulose. They are example of bacterial polysaccharides. Chitin, chitosan, hydroluronic acid. There are examples of animal polysaccharides. Pullan, alcinan, yeast glucans are examples of fungal polysaccharides. Silk, collagen, gelatin, bastin, resilin, adhesives, polyamino acids, soya, gin, white gluten, casein, serum albumin are examples of protein, bioprotein. Acetoglyceride, waxes, surfactants, emulsions, those are examples of biolipids or biosurfactants. Lignin, tannin, humic acid, these are examples of biopolyphenols. Shellac, polygamma-glutamine and natural rubber. Synthetic polymers from natural fats and oil, for example nylon from castor oil. These are specialty biochemicals. The source of this information is uses of biopolymer in medical application. Conference paper, January 2004. Relative production capacities of various biopolymers. In 2015, biopolyester 26%, biopolyethylene terephthalate 17%, PLA 13%, PHA 9%, biodegradable polyesters 8%, biodegradable starch blends 7%, bio-PVC 7%, bio-polyamide 5%, bio-regenerated cellulose 2%, PLA blends 2%, bio-PP 2%, bio-PC 1%, others 1%, total 100%, that is 1,709,700 tons. Biopolymers with high potential. Starch-based polymers are used for packaging. Polylactide or PLA, polybutylene succinate PBS, and copolymers. Polyethylene furanoate, that is PEF, substitute for PET, made from furandicarboxylic acid FDCA and monoethylene glycol MEG. Castor oil PA, it is castor oil based polyamide PA11. Among major biopolymers, polyhydroxyalkonates PHA, polyhydroxybutanate PHB has an emerging market and their demands are increasing in good space. Soybean fiber. Soybean fiber was used as early as in 1930 by Henry Ford for making various soya-based automobile parts. Man-made regenerated protein fiber, soybean protein may be blended with PVA. Biodegradable soybean fibers are biodegradable, non-allergic, microbiocidal. Soybean-based clothing are less durable but soft and elastic. Handle is elastic. Globular protein. Soybean fiber is made from globule protein. It is denatured by alkali heat enzyme and degraded into spinnable dope. Bioepoxy resins. Plastic from petroleum-based epoxy resins are popular. However, bisphenol analogs, that is BPA, and bisphenol A, that is BPS, are not eco-friendly. Excellent green monomers from biosources can be obtained from plant oils, lignin, and furan oils. Epoxized plant oils, specifically soybean and linseed oil. Lignin is a renewable resource that provides phenol and phenolic derivatives. Main problem is the isolation and synthetic of the natural polymers. For example, lignin is a complex compound with a multifunctional nature that makes it challenging to process commercially. This slide schematically shows the manufacture and use of bioepoxy resins. Uses of bioepoxy resins are paints and coating, electronics, aerospace, and additives. Two ways they can be manufactured: non-eco-friendly petroleum-based biphenyl types of compound and with curing agents which are not very green, while other eco-friendly way to manufacture is bio-based epoxy resins and eco-friendly curing agent. Source of this information is given. Recent development of bio-epoxy resins. Normal polyester versus biopolyester. Normal polyester is manufactured by reacting adipic acid and ethylene glycol. These bioethylene glycol can be manufactured by fermentation with yeast and E. coli bacteria that produce biosuccinic acid, bioadipic acid, bioethylene, and then finally bioethylene glycol. Now, polybutadiene succinate (PBS) is a bioaliphatic polyester similar to normal polyester. It is manufactured by reacting succinic acid SA and 1,4-butadiene, that is 1,4-BD. The polyester produces polybutadiene succinate (PBS). It is quite similar to normal polyester. Application of biopolyester are coating, adhesive foams, flexible packaging, agriculture films, composite bags. Sorona, that is manufactured by DuPont, is polytrimethylene terephthalate (PTT). It is a copolymer of 1,3-propanidol produced by fermentation, and terephthalic acid (TPA), dimethylene terephthalate (DMT). These are petroleum derivatives. 37% renewable plant-based input. Polylactic acid (PLA) is a thermoplastic aliphatic polyester similar to PET. It is produced from lactic acid. Lactic acid is dehydrated to form lactide. By ring opening polymerization, it is converted to polylactic acid or polylactide. The renewable raw materials are cornstarch USA, tapioca products, that is root, chip or starch in Asia, sugarcane in the rest of the world. Polylactic acid is known since 1845. It is marketed early 1990. The sequence of procedure starts, then fermentation to form D and L lactic acid, and then it is converted to DL and mesolactides dehydrated, and then it is polymerized to PLA. It is used for plastic, bottles, fiber and film. Polylactic acid, that is PLA, has high strength, good drape, high wrinkle and UV light resistance. Melting point is around 170 degrees centigrade and density 1.25 grams per liter. Limiting oxygen concentration is 25, which is higher than PET and polypropylene. It has reduced flammability. Water uptake is between 0.4 to 0.6%, that is greater than polyester and polypropylene. Polylactic acid fibers are durable under a range of conditions. Applications of polylactic acid fiber: apparel, microwave trays, engineering plastics, biomedical, sutures, stents, dialysis media and drug delivery devices, rigid thermoforms, films, labels and bottles, but no hot fill containers or gaseous drinks. Bacterial polyester. Polyhydroxyalkanoates or PHAs are linear polyesters produced by bacterial fermentation of sugar or lipids produced from wastewater, waste fish or palm oil, biogas and glycerol, producing biogas and glycerol, algae or even aromatic sources. More than 150 monomers are available for thermoplastic and elastomeric materials. Melting point around 40 to 180 degrees centigrade. Polyhydroxybutyrate PHB is similar to PHA. Common types are poly-3-hydroxybutyrate P3HB and poly-4-hydroxybutyrate, that is P4HB. Polyhydroxyallerate or PHB, polyhydroxyhexanate PHH, polyhydroxyoctanate or PHO and copolymers. Biopol Geneca, made by Geneca, it is a PHBV produced by fermentation of PH3B and then copolymerized with PHV. Melt spun, biocompatible and biodegradable fibers are produced which are suitable for surgical use. Drawbacks: expensive, low thermal stability, brittle, primitive mechanical processing is difficult. Biopolyamides, polyamide or nylon, nylon. The biomass resources are castor oil plants, and from that we get castor bean. Castor oil contains sebacic acid having carbon 10. When reacted with fossil diesel, we get hexamethylene diamine C6. When hexamethylene diamine and sebacic acid reacted, we get PS610, that is polyamide 610. This is a bio-waste. Carbon content is approximately 60%. Property: heat stable and low moisture absorption, alkaline resistivity. Application: toothbrush. The information obtained from the Torah Industries journal presentation at Bioplastic, the conference held at Las Vegas, March 2003. Raw materials for biopolyamides. 11 amino undecanoic acid. From 11 amino undecanoic acid we get Pa11. When sebacic acid reacts with hexamethylene we get Pa610. When sebacic acid reacts with pentamethylene we get Pa510. Sebacic acid when you react with picamethylene we get Pa1010. When sebacic acid reacts with tetramethylene we can produce we get Pa410. And when 112 dodecanoic acid reacts with decamphthalene we get Pa1010. Biopolythene or renewable polythene, Bio-PE. It is an important engineering polymer. It is made out of ethanol from feedstock sugarcane, sugar beet and wheat grains. Becomes ethylene after dehydration and decompose to carbon dioxide. The properties identical. These properties of biopolyethylene is identical to conventional polyethylene. Extremely versatile in terms of application. From sugarcane by fermentation and distillation we get ethanol. Ethanol on dehydration we get ethylene. Ethylene on polymerization we get biopolyethylene. Sugarcane capture carbon dioxide, ethanol production and then gain ethylene and gain polyethylene production. Biodegradable polyurethane, PURS. Urethane is a reaction compound of isocyanate and hydroxyl compound as shown in the figure. Thermoplastic polyurethane is a reaction product of diisocyanate and bifunctional polyol and dihydroxy and or diamine chain extender. Some reported enzymatic synthesis of PU by enzymatic polyesterification. Bio-EU, excellent mechanical properties, good biocompatibility. Major application, flexible and rigid foams, elastomers, adhesive surface coatings. Medical, biomass are used for cardiovascular application, polythene insulator in cardiac pacemaker. Biodegradable polyurethanes. Aliphatic diisocyanates are commonly used in formulating biodegradable polyurethanes and polyurethane ureas. Some diisocyanates used in this process are shown in the figure. First one is 1,4-butadiisocyanate, that is BDI. Then 1,6-hexamethylene diisocyanate, that is HDI. And 2,2,4 trimethyl hexamethylene diisocyanate, that is TMDI. Next, ethylene 2,6 diisocyanate hexanoate and methyl 2,6 diisocyanate hexanoate. Next, raw material isophorone diisocyanate, IPDI. And last one, 1,4-cyclohexane diisocyanate, CHDI. Reference is given. Uses of biodegradable polyurethane. It is mostly used as scaffolds for various portions of the body like skeletal muscle, heart muscle, blood vessel, cartilage, bone and nerve as shown in the figure. Sodium alginate fiber, alginate, carrageenan and agar are common seaweed derived products that exhibit interesting film forming properties. Sodium alginate is a polymeric acid composed of two monomer units, L-glucuronic acid and D-manuronic acid as shown in the figure. It is non-toxic and non-irritant. Sodium alginate fiber generates a moisture healing environment, biocompatible and gels on contact with sodium ion, favorable properties for wound dressing. Alginate hydrogels are particularly attractive in wound sealing, drug delivery and tissue engineering application. They undergo ion exchange with other metal ions. Chitin and chitosan. Chitin and chitosan, beneficial biological and antimicrobial properties and having potential for wound healing, are attractive for wound care. Chitin is long chain polysaccharide found in the cells of crustaceans such as lobster, crabs and shrimps and many other organisms including insects and fungi. It is an almost inexhaustible resource as it is constantly produced in huge quantities throughout nature. Advantage of chitin and chitosan. Advantages are they are inexpensive and non-hazardous. They are biocompatible. They bind to mammalian and microbial cells. They are hemostatic, that is, they stop bleeding, fungicides and anti-tumor. Uses. Chitosan is used in a variety of applications ranging from pharmaceutical and cosmetic products, cosmetics, water treatment and plant protection. Chitin and chitosan are polysaccharides similar to cellulose. As shown in the figure, in C2 position, cellulose have hydroxyl group, chitin has acetoamido group, chitosan have amino group. Chitin on deacetylation converted to chitosan. Chitosan is a linear polyamide having reactive amino and hydroxyl group. It chelates many transitional metal ions. This slide shows the flow sheet of chitosan manufacture. The raw material for chitosan manufacture is prawn cells. They are washed, grind and sieved in fine powder less than or equal to 500 micron. Then it is treated with 7% hydrochloric acid for 24 hours. We get demineralized powder. Then it is treated with 10% caustic soda at 60 degrees for 24 hours. We get chitin. This chitin, when treated with 50% caustic soda under nitrogen atmosphere for 60 degree centigrade 8 hours, we get chitosan. The reference is given in this slide. Biopolymers, some achievements. 100% renewable milk protein fibers are completely compostable. Textiles made from it are silky soft, skin compatible, antibacterial, and anti-allergic. Polylactide PLA from corn and tapioca starch fiber. These biopolymers are 100% biodegradable. They are used in packaging, non-woven, and apparel next to skin. Sorona of DuPont, 37% renewable plant-based raw material. Properties similar to polyester and polyamide, very soft, extremely durable and stain resistance. Carpet, apparel, and automobile textiles may be used for it. Polyamide 5.6 from starch, for example, terryl from Cathay for sports apparel and underwear. They have good mechanical properties, high degree of textile wear comfort, and high heat resistance. Moisture absorbency is good. Mass market plastic such as polyester, polypropylene, polyvinyl alcohol can also be manufactured from renewable materials rather than fossil raw materials. Conclusions. Biopolymers are very important in medicine, surgery, and healthcare products. They are 100% biodegradable and produced from natural renewable resources and are recyclable and compostable. They burn without producing toxic byproducts. Innovations possible in all industrial sectors. Biopolymers are not produced from petroleum that drives the global economy. Biopolymer assures a durable economy, but still it is in infancy. Further improvement in properties, economics, and ecological advantage are need of the hour. No or low carbon footprints. The statistics shown in this presentation are old as because the presentation is also quite old. May be updated in future presentations. Thank you for your patience hearing. This presentation contains substantial information about biopolymers, and I hope some of these information will be useful for you. Thanking you once again.